Reservations in two-way slabs by means of yield lines. This video will deal with slabs with a fixed end on all four sides. It will focus on cases 21 to 25. Case 21 is about a rectangular hole with certain conditions on it. We have a rectangle fixed on all sides, and using the yield lines, we see that for the negative bending moments, you will have a yield line on the fixed end, on the four fixed ends. And then we use the 45, 30, 60 rule. So because this is equal to, this side is equal to this side, we have an angle of 45 degrees. So the yield line starts in the intersection of the rotation axis of different parts of the concrete slab. You can do it also for the opposite side of the slab, and then we make the connection between them. So this is the yield line pattern of this slab. We have some geometric characteristics. S1 is of course A over 2 because it is 45 degree, and S2, S3, and S4 it's the same, and they are all A over 2. We will first calculate the maximum bending moment that will be that can be taken by the slab without a reservation. So for all cases 21 to 25, you will have a maximum bending moment without the reservation in the slab. The negative bending moments, in principle, they are different from side to side, or they can be different, and they are different from the positive bending moments. You can fill in for M1, for instance, alpha times M, or for M2, beta times M, then you have a parameter more. But in general, we can say that because of the reinforcement on top and bottom of a slab is most of the time equal, it means that the plastic bending moment, the plastic bending capacity of the slab is the same for the positive and negative bending moments. So that means that M is equal to M1 and M2, which is the most logic way to handle this problem. But it's not mandatory. Yeah? Then we know already that all S1 to S4 is A over 2. We calculate now the work done by the external forces, which is the summation of all triangles, which is S1 times A and S3 times A, and the mean deflection is delta over 3. Then we look at the rectangular portion, which is from there to there, it's B minus S1 minus S3 multiplied by A, and the mean deflection delta over 2. It gives you this amount. Then we look at the work done by the internal forces. We have, for instance, when we start with this bending moment, with the negative bending moments, we have the projection on the rotation axis, which means B. So it's B times M1 times the angle of deflection is delta over S4. We have also B times M, this M here, and the deflection is delta over S4. At the bottom, we have also B times M divided by S2 and B times M1 divided by S2. Left and right, we have M divided by SA times A and M2 times A divided by S1. On the other side, we have A times M2 divided by S3, and we have M times A divided by S3. So this is this formula. When now D is equal to E, and you can get M from this equation, which gives you this equation, which is the M0. Remember, M0 is the bending moment without the reservation in the slab. Let's check this formula. For a square slab, A is equal to B. We use the previous formula by putting A equal to B, and we find Q8 squared over 48, and this corresponds well with the values noted in literature. Now, for an existing slab, there is a reinforcement there before you make the reservation in the slab, so it's AS is equal to AS0. The bending moment, maximum bending moment, is proportional to the load in ultimate limit state times a factor only depending on the geometric characteristics. M is for the slab with the reservation, M0 for the slab without the reservation. Now we can see, because of this, that Q over Q0 is equal to C0 over C is equal to M0 over M, which is logic. For further calculations, we will use EX instead of E. It's just E divided by delta Q. Dx instead of D. And for E equals D, we get M, which is Q dx over dx. And then we define the bearing capacity as 100 times M0 over M. 100 times M0 over M, but it's equal to Q over Q0. Now you see easily that this is the bearing capacity expressed in percentage with regards to the slab without a reservation. Now let's look at case 21. We have the geometric characteristics. We make, for case 21, a rectangular reservation in the slab with certain conditions. The slab is situated in the corner D3, D4, and the size of the reservation is D1 and D2. It's a two-way slab, so it means B must be between A and 2A. The horizontal position of this type 21 reservation is that D2 plus D4, it means this side of the reservation must be at all times on the left-hand side of this yield line and on the left-hand side, and this the back side or the other side of the reservation must be also on the left-hand side of this yield line. So you see that D2 plus D4 must be smaller than B. This is B minus S3, so it will not go further than this. And it must be bigger than S1, so this cannot go further than the other side. Then, of course, D4 must be smaller than S1. And this tip of the reservation must be below the yield line. That means that D4 must be smaller than tangents of this angle, so it must be smaller than S1 over S4 times T3. Vertical position, S4 or D1 plus D3, so D3 plus D1 must be bigger than S4. It means that this side must be on this side of the yield line. And also, top of the reservation must be on this side of the yield line. We make all those conditions to be able to express in a closed formula the maximum bending moment. So now we have filled in the different values of S1 and S2, and these are the conditions that goes with the case 21 reservation. What does that mean? I make a visualization of it. The dark lines means fully restrained. The yellow is the reservation in the slab. And you see the reservation can be like that. You see the right-hand side is left of this yield line. The left-hand side is left of this yield line. Same happens with this. Tip is above the yield line, so it's okay. The other one is below, it's okay. Here too, above the yield line, below the yield line, left of the yield line, and left of this yield line. So now we can have different reservations of type 21. Reservation like this is not allowed because the right-hand side is not on the left of this yield line. So now we can use the method of the yield lines. We have our different geometric parameters. But first, we will define x1. x1 is in fact the horizontal distance between the crossing of the yield line and the reservation with this axis, so like it's indicated here. So it's a little bit confusing. It's not d4. d4 is this. d4 is this, and like that, d4, and x1 is from there to there. Similar on the other hand side, we have here x2 from there to there, and y1 for this to this. So you see x1 equals v3 because this is 45 degrees. x2 is equal to y1. x2 is equal to y1. You see that it's not drawn to scale, so it's a bit confusing. But x2 is equal to y1, and y1, of course, a times d3 times minus a minus d3 minus d1. For the work done by the external forces, we need the maximum deflection in the middle of the slab. This line gives you, or this line here, gives you delta, the maximum deflection, and this is zero from the deflection. So it goes from 0 to delta. So it means that if you use just this simple rule, that the deflection of this, and the deflection here is delta, this deflection is of course delta times d3 divided by 4. Here we have delta divided by S1, which is the maximum deflection, and multiplied by, of course, D4. The same principle is applied on this side. Now we are able to calculate the work done by the external forces. It gives you, first of all, the orange parts, which are composed of rectangulars. And you see, for instance, for the first part, you have d4 times d1, and times the mean deflection. The maximum is d4 delta d4 over s1, and because it's a rectangle, it's half of it. Then we go to this rectangular here, this. You have then, of course, d2 plus d4 minus x1. It's from there to there, minus the x1, multiplied by d3. And the maximum deflection is d3 over s4, and the mean is half of it. So we do it for this part, we do it for this part, and then the last part is, of course, the distance. It's b minus s3 minus d2 minus d4. And then multiplied by a, and the maximum deflection is delta over 2. Then we go to the green areas, which is composed out of triangles. So the mean deflection is delta over 3. And for this right-hand side, we've got a times s3. And for those parts, we have first this triangle belonging to this axis of rotation, this triangle belonging to this axis of rotation, and so on. So we have those 4 terms. This is getting, when you fill in the different parameters, it's getting very lengthy, this formula, and not practical to use. So we've cut this formula in some pieces. It doesn't matter how you do it, it's just to make it easy to write it down. So I call it a factor h, which is equal to this. And then ex can be written if you order it to y1 squared. Then you see this is the formula for ex. You can calculate now the work done by the internal forces. And this is, for instance, for this negative yield line, B divided by S4. So it's the length of the yield line projected on the axis of rotation with an angle of rotation equal to delta over S4. So it's D over S4 because the delta is there. Then the same for this negative bending moment, A over S3. This is B over S2, and this is A over S1. Now we will take care of this yield line projected to this axis. So the total length is from there to there. So it's B minus D4 minus D2. And the angle of rotation is on this side, delta over S4, and here delta over S2, which is those two. Then we got this small piece here, which is reacted to this axis. So we have a total length of x1 divided by S4. And the other side is they're projected on this axis. This line is projected on this axis. So you have D3 divided by delta over 1. And then the same for the bottom line, x2 over S2 and y1 over S1. And we fill in the different parameters and we find this formula. The bending moment then is calculated by putting B equal to B equals to E, and then we get M out of it, which is this. Of course, we must remember there are some conditions to this case 21 hole, the horizontal position and the vertical position. Now let's make an example, a rectangular slab with a depth of 180 millimeters and a concrete cover of 40. There's a fixed load of floor finish of 2 kilonewton per square meter and a live load of 5. And we want to know what is the needed reinforcement considering the reservation in the slab. So we calculate the load in ULS, which is 1.35 permanent loads plus 1.5 mobile loads, give you 16.3 kilonewton per square meter. These are the different parameters of the slab and the reservation. We know that S1 is equal to S4 and so on. It's A over 2 or 3 meters in our case. We calculate Y1, straightforward, 2.4 meters. We check the horizontal position. This was the condition. So D2 plus D4 is 4.8, and it should be between 3 and 9 minus 0.5 times 6 is 6. So 4.8 is between it, so it's okay. The horizontal position is okay. Second condition is also fulfilled, and the third condition also. Now we look at the vertical position. Vertical position, D1 plus D3, 3.6, and it's bigger than 3. So this is okay. Then this is also fine. We can now calculate the maximum bending moment, assuming, of course, that the reinforcement of top and bottom is equal. And we calculate the parameter h, calculate EX, just straightforward, fill in the different numbers and with the different parameters, and you got 17.35. dx, we find 18. So M is Q times EX over dx. It gives you 15.7 kilonewton meter per meter. Now we will convert it into reinforcement. The lever arm in its direction is then 136 millimeter. In the y direction, 128. So the mean lever arm is 132. The needed reinforcement is then the maximum bending moment divided by the lever arm divided by the yield strength and multiplied by 1.1 because yield lines is an upper bound method. So we have now 334 square millimeters per meter, and with 8 diameters, 8 per meter, it will be fine. Remember, there is bottom reinforcement in X direction and Y direction. So you have 4 times this. Now let's go to a second example. You have an existing slab, and it's reinforced in two directions. And you know that the top reinforcement is equal to the bottom reinforcement. Now, it is asked if it's possible to make a reservation in this existing slab of 0.6 by 3.3 meters. And it's situated like here. For instance, a reservation for electricity cables or other elements. We just bear in mind that we do not know the original load of the slab, and we do not know the total amount of reinforcement already there. So how do we do it? Well, we calculate the maximum bending moment without the hole. So we assume that the slab was calculated in a right way, correctly. So we take the maximum bending moment without the hole, but we don't know Q, the load. So we divide M0 by Q. And what's left is only depending on geometric characteristics. So M0 over Q is 1.05. We can now calculate the maximum bending moment with the hole. It's M over Q. You have 1.086. That means that bearing capacity is 97%. So in fact, by making this hole or this reservation in the slab, you have a small loss of 3% in the bearing capacity. Now, the formulas you can do a lot with it. I give you an example. For instance, you can calculate where should this reservation be for not having any loss in bearing capacity. Well, if you move this reservation to the left to a maximum of 1.5 meters from the edge, then it will result in a bearing capacity which is bigger than 100%. So by just moving the reservation, you do not have any loss in bearing capacity. Now let's give another example how you can apply those different formulas. We have, for instance, a reservation of this type. Alpha 1 is 0.1. It means that this is 1/10 of the side. Alpha 3, the position here is 0.45. So in fact, because this is 0.1, this is 0.45, it means that it is right in the middle. So this is centric here. Alpha 4 is 0. It means it's to the left-hand edge size. And now we have a reservation going from there till there. So the width of the length of the reservation increases and increases from alpha 2 from 0.5 to 1. So it means from 0.5a or 2 is between 0.5a and 1 times a. So this is this situation and this situation. And the question is, what is now the influence on the length of this reservation on the bearing capacity slab? We first look at the different parameters. Alpha 4 is D4 divided by A, but D4 is 0. It's against the left-hand side of the support. We have alpha 1 and alpha 3, and we know that alpha must be 1 and 2. First thing we notice is that this reservation, we have put D4 is equal to 0, means that there is no yield line here. So where the red part is. So in fact, we should adapt our formulas and subtract this. And instead of the length A, it has the length A minus D1. And this is the loss, in fact, this is the factor that is going to influence the amount of G, but for relatively small reservations, the error you make is smaller than 1%. But in fact, you should adapt your formula. The horizontal position, we will check if this hole reservation fulfills the conditions of case 21. We look at the horizontal position and we see that alpha 2 is variable here in our example. So alpha 2 must be between 0.5 and alpha minus 0.5. That's the condition on this reservation. The second condition is okay. The other condition is also fine. We look now at the vertical position. This is fulfilled, and this is also correct. So we know now that this is a case 21 reservation on the condition that alpha 2 is situated between those two limits. We can now calculate for the difference values of alpha 2, or we fill in the known parameters, and we can calculate the bearing capacity of the slab, and it's defined as 100 times m0 divided by m. And m0 is the bending moment without the reservation, and m is the bending moment with the reservation. So we got then a function of alpha, b over a, and alpha 2. On the x-axis, we put the range of alpha 2, and on the y-axis is the bearing capacity. There's a condition that on the case 21 reservations, and on this particular case that we are studying, and the condition was, according to the previous slide, that alpha 2 must be between 0.5 and alpha minus 0.5. It means that the validity of each function here, like stated there, depends also on the factor alpha. That's why you see suddenly a drop. So for instance, for alpha equal to 1.1, it is only valid in this portion, and when alpha 2 is bigger than 0.6, it's not possible anymore. You can easily see that if this is 1.1 minus, so you see that this equation cannot be fulfilled. So on the right-hand side, it's not valid. And it differs from each curve, each different value of alpha. Let's give an example to make it clear. When alpha is 1.5, that's the black curve. You see this point, this is 6 and this is 9, so alpha is 1.5. So you see that the bearing capacity is 102.4 for alpha 2 equals 0.5. We are there on the black curve. Then we move further on for alpha 0.75. You see that this reservation gets bigger. It gets from 0.5 times A to 0.75 times A. You have this point with a bearing capacity of 101.5. And then you have this situation where alpha 2 is equal to 1. So it's this form of reservation, and you have a bearing capacity on 100.5. So you see when this is 1.5, the upper limit is 1, the under limit 0.5. So you go from 0.5 to maximum 1. After that, it's not possible anymore. Okay. Now, you notice in this little study, we see immediately that for reservations of type 21, or the type that we have studied now, there is no loss in bearing capacity for square slabs. So if alpha is 1, all values are above 100%, so there is no loss in bearing capacity with this type of reservation, which is something you should not expect to happen. So for a bearing capacity bigger than 100, because that's in fact what you want, you don't want to lose bearing capacity by making a reservation in the slab. So you can define alpha 2 max, which is the value of alpha 2. When alpha 2 is equal to alpha 2 max, then the bearing capacity is 100%. So you must always have, or you must try to have an alpha which is smaller than alpha 2 max. You can, in the formula of the bearing capacity, you put it equal to 100, and then you arrive at this formula. You put it into a graph, you see in function of alpha, and the y-axis is alpha 2. We know that alpha 2 has a lower limit and an upper limit. And the upper limit is, of course, alpha minus 0.5, which is this dotted line, the upper limit. And it has a lower limit of 0.5, which is independent of alpha. So now all values between those black lines are valid for alpha 2, but the others are not valid. And what we see, which makes it interesting, is that for this limit, that point, you put alpha 2 max for equal to alpha minus 0.5, and you can solve it for alpha. You see that for alpha equal to 1.54, you reach the upper limit. So left of this is not valid. On the right hand side, it's not valid anymore. So what can we do with this graph? Well, if you want to calculate the bearing capacity of a slab with alpha 1.8 and alpha 2 equals to 1, then you have here in this area 99% of bearing capacity. So you are touching the bearing capacity. When you go below this red line, you do not touch the bearing capacity. So that's the meaning of this. Above, you touch the bearing capacity. Below, you do not touch. And here, this point 2, you do not touch the bearing capacity. It means that you should go for this area. All combinations of alpha and alpha 2 in this area give you a reservation which is not lowering the bearing capacity. That's the way you can use those type of formulas.